A very good morning to all the students. I am Dr. HimaBindhu from the Department of Mechanical Engineering, and I'll be dealing with the subject robotics. And my today's topic is problem solving on RPR arm of a manipulator. Right? Firstly, let me read out the question. The tooling manipulator is applying a force vector 3F with the end effector. Find the required joint torques as a function of configurations and of the applied forces. That is, we need to find out the joint torques and function of configuration for the forces. So here firstly we need to determine the force equation, that is Fx, Fy and 0. If we are having only two axes, x and y, and 0 will be considered as, z will be considered as 0. So Fx at force x-axis, Fy force at the y-axis, and force at the z-axis is 0. Right? That is F2 of 2 is equal to Fx, Fy and 0. Whereas the N2 by 2 is equal to L2 x2 into Fx into the force, which will be written as 0, 0, L2 Fy. Right? When we consider the frame 1, right, when we consider the frame 1, then F11 is equal to the rotational matrix, that is C2 minus S2 0, S2 C2 0, 0, 0, 1 into this particular F2, that is force with respect to the frame 2, which will be equal to C2 Fx minus S2 Fy, or S2 Fx plus C2 Fy and 0. And this particular final derivative for the number 1 to 1 will be equal to 0, 0, L2 Fy plus L1 x1 plus 1 F1, which is equal to 0, 0, L1 S2 Fx plus L1 C2 Fy plus L2 Fy. Right? Now, for this we write the torque as, right, the force is already been determined in this form. Next, we write the torque as T1 is equal to L1 S2 at force x at x-axis plus L2 plus L1 C2 into Fy. Right? Whereas torque 2 will be equal to L2 Fy. Now, this particular relationship can be written as a matrix operation where we are considering torque is equal to L1 S2 and L2 plus L1 C2 0 L2 into Fx of Fy. Right? That is, this particular relationship can be written as the matrix operation. That is, torque is equal to L1 S2, L2 plus L1 C2 or 0 L2 into Fx and Fy. Now, this is about the two-link manipulator, how we calculate the force and the torque. So, this is how we calculate the force and this is how we calculate the torque. Right? Now, next, moving on to the next problem, that is how we determine the analytic Jacobian of a planar 2-hour arm. Right? When we have a planar 2-arm arm, how do we write the analytic Jacobian for a planar matrix? Now, as we can see in this figure, we have two links, link 1, link 2, to which the end effector is being fixed. Now, link 1 is being rotating at an angle Q1 and link 2 is being rotating at an angle Q2. Right? Whereas the end effector is being rotating at an angle of pi. Right? And this is the Px and this is the Py. Now, when we need to calculate the Jacobian matrix here, first we need to find out the direct kinematics. With respect to the direct kinematics, we need to find out Px and Py. So, with respect to the direct kinematics, the Px and Py is being determined as L1. See here at Px, L1 cos Q1, right? L1 cos Q1 plus L2 cos Q1 plus Q2, right, with respect to the x-axis. And with respect to y-axis, what we are writing? L1 sine Q1 plus L2 sine Q1 plus Q2. That has been determined as y is equal to Q1 plus Q2. Right? This is Q1 plus Q2. Right? So overall, the R has been written as y is equal to Q1 plus Q2. Now, when we take the angular axis, right? When we take the angular axis, then Px dot will be equal to minus L1 sine Q1 dot, it will be this reverse, right? Minus L2 sine 1 to Q1 dot plus Q2 dot. And Py dot will be written as L1 C1 Q1 dot plus L2 C12 of Q1 dot plus Q2 dot, where this pi dot will be written as omega z, which is equal to Q1 plus Q2 dot. Here all the rotations will be occurring around the same z-axis, right? All the rotations will be occurring around the same z-axis. Now for this, the Jacobian will be written as JR of Q is equal to minus L1 sine theta 1 minus L2 sine theta 1 of T2 minus L2 S12, or L1 C1 plus L2 C12 or L2 C12, where it is written as 1 and 1, right? Where this is 1 and 1. So the given R is a 3 by 2 matrix. So this particular matrix, whatever we have written, is a 3 by 2 matrix where R dot will be written as JR of Q into Q dot, where R dot will be written as JR of Q into Q dot. That is, the analytical Jacobian for a planar 2R manipulator will be written as R dot is equal to JR into Q dot. This first we will be we will be determining for the normal R, then we will be determining for the angular, and then we will be writing the matrix, and overall the R dot will be written as JR into Q dot. Right? Now the next one, when we consider the RRP robot, right? When we need to analyze the Jacobian of a polar RRP robot, then here we can see that here we have x-axis, y-axis, and here we have the z-axis. So this is one link and this is the other link. So this is moving at a distance d1, right, at an angle of q1, and this is moving at a distance q3 at an angle of q2. Right? So here we will be writing the direct kinematics, that is R is equal to P. Right? The direct kinematics here R is equal to P, where we are writing it as Px. For Px, right? For Px we are taking, for this particular Px, we are taking Q3 Px here. Right? Q3 cos theta 2 cos theta 1. Right? Q3 C2 and C1. For Py, what we have considered, this is Py, right? For Py, we have taken Q3, C2, C1, right? C2, S1. And for Pz, we have determined the distance of how much it is moving, right? Pz is equal to D1 plus Q3, S2. So this overall is being written as function of R into Q, right? This overall will be taken as function of R into Q. Now, taking this the derivative with respect to the time, taking this particular derivative with respect to time, we are writing v is equal, velocity is equal to p dot, which is equal to minus q3 into c2 into s1 minus q3 into s2 into c1 c2 c1 q3 c2 c1 minus q3 s2 s1 c2 s1 0 q3 c2 and s2 into q dot, which would be equal to the Jacobian of R with respect to q into q dot, same as this one, 2r armature, where this overall is being written as dou fr of q by dou q, which requires doing only partial derivation with respect to the joints q1 to qn, right? With respect to the joints q1 to qn. Right? Now, when we consider the geometric Jacobian, that is when we consider a 6 by n matrix, right? When we consider a geometric Jacobian, which is a 6 by n matrix, then the velocity of the end effector and the instantaneous velocity omega e will be written as JL of q into JA of q into q dot, right? JL of q into JA of q into 2 dot, which is a 2 by 2 matrix, 6 by 2 matrix, right? Now JL1 into q, so on up to n number of matrices into JA1 of q into n number of matrices into q1 dot, so on up to qn. Now the superposition of the fx will be written as VE is equal to JL1 into QQ dot plus so on up to JLN into QQ dot n. Whereas omega e will be written as JA1 into QQ dot plus so on up to JAN into QQ dot. Now, to contribute to the linear E velocity due to Q dot, we will be taking this particular equation. To contribute to the angular EE velocity due to E, we will be contributing this particular equation. Now, the linear and the angular velocity belongs to the vector space in RQ with respect to the RQ. Right? So, here the Jacobian, geometric Jacobian planar for the 2R arm when the DH table is being given. When the DH table is given, how do we write the Jacobian matrix? Where the joint is as alpha 1 D1 A1 into theta 1 for link L1 and joint 1 and 2 we have 0 0 0 0 L1 L2 Q1 Q2. So the equation will, the Jacobian matrix will be written as A1 to 0 is equal to C1 S1 minus sin theta 1 cos theta 1 0 0 L1 cos theta 1 L1 sin theta 1 with respect to P01 0 0 1 0 0 0 0 1. So this is how we write the matrix with respect to this particular table. Now the Jacobian of Q will be written as Z0 into P0E or Z1 into P1E or Z0 and Z1, where this will be written as a 1 by 3 matrix, that is 0 0 and 1, right? This has been written as 0 0 and 1, whereas A2 of 0 will be written as C12 minus S12 0 L1 C1 plus L2 C12 or S12 or C12 0 L1 S1 plus L2 S2 for POE, right? For POE from the point P to OE. E, right, from the point E to O. So here overall the equation will be written as P1E will be equal to POE minus P0 to 1. That is, all the computations can be made numerically, evaluating first the direction kinematic terms, right? Next, moving to the transformation of the Jacobian matrix. Now, when we have the different forms of links, how do we do the transformation of this particular Jacobian matrix? Firstly, we need to choose RFP, which is equal to RFI of Q. That is, these are the links where it is at an initial position RF0, and this is the link which is moving at RFY, right? And this is the final in the B position, where we need to choose E is equal to this particular equation. E is equal to OJ into Q. E is equal to OJ into Q. Now for this particular equation, we will be writing the velocity and angular velocity as Jn of 0 Q into Q0, same as the previous one. And we write the matrices as R0B 0 0 RB to 0 or I0 S into R1 V and N. So here we will be determining the JE with 2B of Q into Q dot. So this is how we write the transformation of the Jacobian matrix, right? In order to do this particular equation, the mobility analysis is very important. So when we are doing the mobility analysis, we need to define it locally first, right? After that, we need to depend upon the current configuration. When we are defining it locally and when we are depending on the current configuration, then we can find out Q, that is rho of J is equal to rho of J into Q, or R of J of Q, or n into j power t is equal to n into j power t into q, where r is nothing but the subspace of the generalized velocity, which is instantaneously realized by the robot end effect r with respect to the joint velocities q dot and the current q, right? Q dot is equal to joint velocity and q is equal to current, right? If rho of jq, if rho of this particular rho of jq is equal to m, right? The end effect r can be moved in any direction, and that will be written as r power m, right? If rho of j of q is equal to m, the end effect r can move in any direction, and that will be written as r power m. If rho of j of q is less than m, right? If rho of j of q is less than m, then the r power m in which the end effector cannot move, then the r power m cannot move in any direction, right? If n of j of q is not equal to 0, that is, if it is non-zero, the joint velocity q that produces 0 and the end effector is a self motion. It is a self motion, right? Now, when we consider this particular mobility analysis for a planar 3R robot, then L1 will be equal to L2, which is equal to L3, which is nothing but 1. Right? L1 is equal to L2 is equal to L3, which is equal to 1, where N is equal to 3 and M is equal to 2. And this particular matrix will be written as V is equal to P dot is equal to minus S1 minus S12 minus S13, or minus S12 minus S123, or minus S123. So that is, overall we will be getting J of Q into Q dot in R power 3, right? J of Q into Q naught into in R power 3. Now when we consider two cases, when we are considering case 1 and case 2. Now when we are considering these particular two cases, then Q will be considered as Q is equal to 0 or pi by 2 or pi by 2. That is, we write it the equation as J is equal to minus 1 and 0, 0 minus 1 and minus 1. Right? That is, J is equal to minus 1, 0, minus 1, 0 and minus 1, or J power T. When we consider case 2, Q is equal to pi by 2 or 0 or pi. Right? So that equation will be written as J is equal to minus 1, 0, 1, 0, 0, 0. Or rho of J is equal to 2 is equal to M, or rho J power T is equal to rho J is equal to 2. That is, for case 1, we write the matrix as R of J is equal to 1, 0, 0, 1, that is R square. Or for case 2, Nj is equal to 1 minus 1 minus 1, that is dim of dimension of n of j is equal to 1, which is equal to n minus rho of j, where n minus m we are considering, right? That is, r j power t will be written as 110 or 010. And this will be written as dim of r j power t, which is equal to 0, that is rho j is equal to m, right? So this is how we calculate the mobility analysis for a planar 3R robot. Right? We have seen how the mobility analysis in the task is being written, and how the matrices are being written, and how the geometric Jacobian of planar 2R arm will be written, and how the generalized Jacobian matrix will be written in form of 6-band matrix, or how we do the analytic Jacobian for RRB robot, and how we do the Jacobian of a planar 2R manipulator. So this is all for today. Signing off for today, Dr. J. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.